Testing, can you hear me? So I'm going to be reading Discrete Math again. I'm just going to be reading the next chapter. Let me just change to full screen. All right. Wait a minute. Wait a minute. Okay, so last time I was reading about coloring, and this stream I will start this chapter relations and graphs. After complete, okay. Section preview, consider the three spinners below. If you and a friend each pick a different spinner and spin them, we can consider the nine possible outcomes. For example, between spinners A and B, the outcomes are two. Wait, between spinners A, B. Okay, so 2, 1, or 2, 6, 2, 8, 4, 1, 4, 6, 4, 8, 9, 1, 9, 6, 9, 8. This suggests that spinner A will win 5 out of 9 times. What do you mean by win? What do they mean by win? Will win 5 out of 9 times. 1, 2, 3, 4, 5. Or they mean like when an A gets a high number? In this section, we will explore a generalization of a graph called a relation. We will see how a relation can be represented by a graph and how a graph can be used to represent a relation. We'll also consider some properties that a relation might have. Okay. In a given month, some days are more similar than others. For example, the third of the month is more like the 24th than it is like the 15th. What does this possibly mean? We'll explore two ways in which this could be true. We say that two numbers between 1 and 31 are related, written A related B. What do you call this symbol? If their difference is a multiple of 7. Oh, so they're defining a relation that the two numbers are related if their difference is in a multiple of 7. So, for example, 3 is related to 24 since 24 minus 3 is equal to, is a multiple of 7. But 3 is not related to 15. Which of the following are true? That is, which of the following pairs of numbers are related as we have defined above. So 4 and 14 are not related. 14 minus 4 is 10. 14 minus 7 is 7. So these are related. This is related. Uh, 24 minus 17. I think they're related. Yeah. 17 plus 7 is 24. Yeah, I got the point. Which of the following statements are true about the relation in this case? A is related to A for every number A. This is true. Uh, for any number A and B, if A and B are related, then B is related to A. Or they changed the question. Which of these relations are reflectives? The variable x, y, x naught, y naught represent integers. X is related to y if and only if x plus y is positive. Wait, is there some context I'm missing? They're giving me a different question. Okay, let's just skip that. When you divide a multiple of 7 by 7, you get a whole number. If you divide another number by 7, you can either write the result as a decimal or as a quotient and a remainder. For example, 19 divided by 7 is 2 with a remainder of 5. Since we can write 19 is equal to 2 times 7 plus 5. The remainder is called the modulus. When programming in Python, the modulus operator is written as this percentage. For example, 19 percentage 7 is 5. Find all numbers A between 1 and 31 that are 5 mod 7. That is, find all A such that A modulus 7 is equal to 5. Why is it giving this? Okay, let's just skip this then. A graph is a way to represent some ways that different objects are related. You have seen how to use graphs to represent which people are friends or which classes have time conflicts or which radio stations are too close to have the same frequency. Not all ways in which things can be related can be presented by a graph, however. In this section, we will consider the more general concept of a relation and see how those might be related to graphs. Consider the example of the relation between students and classes that holds when a student is in that class in a particular semester. This is a relation between two different sets. If we used a graph to illustrate this relation, the graph would be bipartite, since two students are never related to each other and two classes are never related to each other. A graph is really a set of vertices and a set of edges. Each element of the set E is a two element subset of B. If we want to draw attention to the bipartiteness of the graph, we can split up B into two sets and write G is equal to ABE. This notation, the graph would be for the graph to be bipartite, we want each edge to be a pair AB, where A is an element of A and B is an element of B. In other words, each edge is an element of the Cartesian product A and B, written like this. AB is an ordered pair. Why does it need to be ordered? Can it not be a set? Even this, shouldn't it be a set? Because A, B, B, A, the relation is like same, right? The order shouldn't matter. Another way to say this is that the set of all ordered pairs of elements from A and B. So the Cartesian product AB, so set A and set B gives ordered pairs. There is only one subtlety we should point out. The bipartite graph we have described really has directed edges from A to B since we are considering ordered pairs. Okay. These are directed edges. One definition of a graph has edges as two element subsets of vertices and subsets are not ordered. As long as A and B are disjoint sets, there is no confusion here. But we see relations in which A and B share some element, but we still care about the order. More on that soon. This example exactly illustrates what a general binary relation is. Here is a careful definition. A binary relation is a set of ordered pairs. We say the binary relation is a relation on sets A and B provided the ordered pairs are a subset of A times B. We say a binary relation is a relation on set A provided the ordered pairs are a subset of A times A. Now that A times A is just a set of all ordered pairs, where both coordinates are elements of A from A. Consider a set A of students and a set B of classes. Say A is Al, Bob, Kat, Dirk, and Eva, and B is calculus, discrete statistics. Everyone except Dirk is in calculus. Bob and Eva are in discrete, and Al, Kat, and Dirk are in statistics. We can define a relation T of is taking A and B that holds a student and class precisely if that student is taking that class. Write this relation as a subset A and B and draw its bipartite graph. Hold on. Select this. Copy. Uh, so we have set A, set B. I'll just write it like vertices A, B, C, D. These are the vertices representing people. Calculus, capital C, capital D. These are the classes. These vertices are classes. We have a directed edge. So we have a pair from A to B. So everyone except Dirk is in calculus. We have this, this, this. Uh, Bob and Eva are in discrete. Bob. Did I miss Eva? A, B, C, D, E, yeah. Bob and Eva are in discrete. Eva is also in calculus. Al, Chad, and Dirk are in statistics. Al, Al, can I, uh, never mind. Al, Cat, and Dirk. Cat, Dirk. Is Dirk only in statistics? Seems like it. Define a relation T. I forgot how you define the relationship again. T. Y. Wait, how do you define a relation again? Oh, so a set of ordered pairs. That's how you define it. Calculus, statistics. Okay, okay. And they drew the graph like this. Consider a relation M for is multiple of on the set A. Write this set write this as a set of ordered pairs. Does this relation create a graph? So we have A 1, 2, 3, 4, 5, 6. 2.6.4. 1, 2, 3, 4, 5, 6 is a multiple of 1, 2, 3, 4, 5, 6. So is a multiple of 6 is a multiple of 3. Do I write it like this? 4 is a multiple of 2. 5 is a multiple of 1. 6 is a multiple of 6 is a multiple of 1. All of them are a multiple of 1s. 3. And like that. Does this relation create a graph? I mean, yeah, it does. Uh, can we do 6 as a multiple of 6, like on itself? In that case, it won't be a graph, right? We know that 6 is a multiple of 2. Wait a minute, did I miss 2? Yeah, I did. But what about this? All of them are a multiple of each other, right? So it's not a graph. 6 is not a multiple of 4, so the pair 6, 4 does not satisfy the relation. More precisely, we say that 6, 2 is part of M, but 6, 4 is not. So 1, 1, 2, 1, 1, 1, 2, 1, 2, 2, 3, 1, 3, 3, 3, 1, 3, 3, 4, 1, 4, 2, 4, 4, 5, 1, 5, 5, 6, 1, 6, 2, 6, 3, 6, 6. This relation is not a graph for two reasons. First, the elements are related to themselves, and second, the order of the element in the relation is not symmetric. 6 is related to 2, but 2 is not related to 6, for example. We can, however, still draw something like a graph to illustrate this relation. Wait for the previous one. Draw its bipartite graph. So the graph is, the edges in the graph are not directed, right? So when we are drawing a graph, but this is not a graph because the edges are supposed to be directed. A binary relation R on sets A and P can always be turned around to give a relation on sets B and A. That is, R is how things in A are related to things in B. Those things are in B are related to things in A, just in the inverse way. We call this new relation the inverse of R. Given a binary relation R, define R inverse to be the inverse of R as a set BA where AB is a relation. The relation T from example 2.6.3 said that a class student was in a particular class. The inverse relation says that the class has a particular student in it. For example, calculus L is an element of T inverse. Graphically, there won't be any difference in the picture, although we could put the set of classes on top and students on bottom. The relation M in example 2.6.4 gave us that, for example, 6 is a multiple of 2. For the inverse, we have 2, 6 for the inverse multiple, which means 2 is a factor of 6. For this example, we have represented a relation as a directed multigraph. A directed multigraph. Wait, what's a multigraph again? Uh, Control F multigraphs. Had double edges because they really are two bridges connecting a particular island to the near shore. We call these objects multigraph. Oh, if there are multiple edges for the same pair of vertices. Wait a minute. This is not a multigraph. But for the inverse, it might be right. The graph of the inverse will look exactly the same, but all the arrows will point in the opposite direction. But it's not a multigraph, right? Another way to create a new relation is to two combine two relations. Suppose in addition to the is taken relation from example 2.6.3, we define a relation is taught by that matches up each course with its instructor. Perhaps Professor X teaches calculus. In that case, since Al is taking calculus, calculus is taught by Professor X. We can conclude Al is taking a class with Professor X. Let R be a relation from set A and to B, and S be a relation from B to C. The composition of R and S is composition is AC is an A to A times C. AB is an R. Oh, so the composition is AC, right? R will contain AB, S will contain BC, and then AC is in the composition. Now the order in which we wrote the two relation, it's S dot R, not R dot S. The reason we do this, which might seem backwards, is that it agrees with the usual notation for the composition of functions. In fact, functions are nothing but a specific type of relation. I dot B dot T. So we evaluate the R first, and then we evaluate the S. So all the S relation from the R. So we look at the R relation and take out all the ones that are in S as well. Write out the relation P dot T, composing the relations of example 2.6.3. And so P is equal to calculus Professor X. Wait a minute, hold on. Calculus Professor X, Discrete Professor S, Statistics Professor X, Statistics Professor S. And then we are saying that the statistic course is co-taught by Professors X and S. So going back to this, 2.6.7. So A, B, and why is it D? Wait, what's the previous relation called with the professor and everything? So relation T is with A and B, right? A to B. Relation P is from course to calculus. So we will have Professor X. Let's call it set Z, Z of professors. So we have X, L, S, X, and P, X, P, L, and then P, S. So we have C, D, S, C, D, S. So what do we have? Calculus, Professor X. So it's going from calculus to Professor X. Discrete, Professor L. Statistics, Professor X. And then Professor S. So P dot T is A px. So I'll just write A px. And then we have A ps. And B, I think B was Bob. Bob px. Bob pl. There's no third one. Px. PS. D px. E px. E pl. Professor X. AX, AS, PX, PL. AX, AS, PX, PL. CX, CS, DX, DX. Wait, what? No, it's a DS, right? Sorry, it's DX and DS. DS, DX, DS, EXL. Something interesting often happens when you compose a relation with its inverse. You might have seen something like this for functions in calculus and algebra. So AX has an inverse function n of x, and we know that function with its inverse gives x back, but functions are relation in which every input has exactly one output. So perhaps it is not surprising that compromising with an inverse just gives you the identity function. When inputs can have multiple outputs and outputs can have multiple inputs, then we have something more. Properties of relations. From this point on, we will consider relations on a single set. To help understand these relations, let's consider some basic properties a relation might or might not have. A relation, wait, what? Let R be a relation on a set A. On the set A, we say R is reflexive provided A is in the set. R is symmetric provided for all A be in the set. We also have BA. R is transitive for all A, B, C. If A, B is in there, then B, C is in there. Okay. Equivalence relations. Now we will do something very typical for mathematics. We will look at our most common types of relations, consider what properties these have, and then classify other relations that have these properties as a specific class of relations. The relation we are most familiar with is equality, which properties of relations does the equality relation possess. Consider everything is equal to itself, so equality is reflexive. If A is equal to B, then B is equal to A, so equality is symmetric. If A is equal to B, then and B is equal to C, then A is equal to C, so equality is transitive. What other relations are reflexive, symmetric, and transitive? Exactly those relations that behave like equality. Call such relations equivalence relations. A relation that is reflexive, symmetric, and transitive is called an equivalence relation. Another example of a type of a relation that is modeled after a classic relation is partial order. That this is a relation that is reflexive, anti-symmetric, and transitive, just like less than or equal to. So transitive, reflexive, but not symmetric. Prove that the relation what is this, which holds of two integers if their difference is even, is an equivalence relation. That is uh, how do you A equal B if and only if B minus A is equal to 2k for some integer k. So we need to prove that this is, let's see, example 2.6.15. A minus A is equal to 0, which is equal to 2k if k equals 0. Therefore, there is an equivalence relation with itself. So it's reflexive. Reflexive. Did I write it properly? Reflexive. Reflexive. Yeah. Symmetric. Wait. Assume A minus B is equal to 2k naught. Then A minus B is equal to 2k naught minus 2a, right? Minus A plus B is equal to 2k naught minus 2a plus 2b, right? B minus A is equal to 2 times k1. Therefore, A to B implies B to A. This is symmetric. So symmetric is done, transitive is done. We have, sorry, transitive is not done. A assume is equal to 2k1 and B minus C is equal to 2k2. A minus B plus B minus C is equal to 2k1 plus 2k2. Okay, we take the 2 out and k1 plus k2 becomes k3. Therefore, A minus B and A implies, sorry, wait. B implies A, C. Transitive. So there we did it. This example is too obvious. Given any relation, we can look at a set of examples that are related to a particular element. For the staking relation, we can ask what classes L is taking. For the is multiple, we can ask which number is a 6 is a multiple of. One way to study the relation is to study the set of things related to each element. Given any relation R, okay, one way to study relation is to study the set of things related to each element. So we have equivalence classes and partitions. Let R be a relation on set A. Let A be an element of A. The relation class of A written in square bracket is a set of all elements B such that AB is in the relation. That is, but how do we tell the relation? So the variance class of A, the relation class of A, R be a relation on set A. Okay, find the relation classes for the is multiple of relation on the set A. 2.6.18. Oops. For 1, we have all the sets. So R is a relation on A. 1 is equal to the what? Relation class of A. The relation class of 1 itself, 3, 4, 5, 6. The relation class of 2 is 2, 4, 6, for 3. It's 3 and 6. Wait, it's a 1 as well. No, no, it's not 1. Is it 1? Wait, am I getting this wrong? Uh, is a multiple of. No, no, I think it's the other way around. No, I think I got this wrong. 1 is a multiple of itself. 2 is a multiple of 1 and 2. 3 is a multiple of 1 and 3. 4 is a multiple of 1, 2, 4, 5, 5, 6, and 2, 3, 6. This is it, right? 1, 1, 2, 1, 3, 1, 2, 4, 1, 5, 1, 2, 3, 6. Find the equivalence. Okay, I'm not doing that. -3, -1, 2, 3, 5. For 2, we have -4, -2, 2, 4, 6. Actually, I think we are done. While 3, 4, and 5 and so on are all completely valid equivalence classes, the elements are all related to 3. The elements that are all related to 3 will be exactly the elements related to 1. Since 1 is equal 3, this because the relation is transitive. For the is a multiple of relation, which is not an equivalence relation, some elements belong to more than one relation class. But for equal, which is an equivalence relation, every element is in exactly one equivalence class. This is no accident. To make sense of this, we will define a new term. Given a non-empty set A, a partition of A is a set P of non-empty subsets of A such that every element of A is in exactly one element of P. A partition of A is a set P of non-empty subsets of A, such that every element of A is in exactly one an element of P. Partition of A is a set P. Oh, P is a set of subsets of A. Now I understand. So, like, if A is like this, P is like, it's a set of set. Set A, B, C. And then we have set D. I think every element of A is in exactly one element of P. So it's only in one of them. You can't have D here and D here. And all elements should have to be included. That definition has a lot of symbols and set involved, and it's not really complicated. A partition is a way to break up a set into disjoint subsets that cover the whole set. That the subsets are disjoint means no element is in more than one subset. Give a few partitions of the set. So 1, 2, 3 can be in one set, 4, 5 can be in one set. Oh, that is the first example. Uh, it is sometimes a little confusing to think of elements of a partition as subsets since the partition is a set. A set of sets can be difficult to talk about. We will call the partition a collection. We sometimes call a partition a collection in each element of the partition, parts or blocks. Now the big idea: for any equivalence relation, the equivalence classes form a partition. And for any partition, we can define a relation or inner subset, which will be an equivalence relation. We've already seen that the equivalence classes of this form a partition. Let's go to the other direction. Okay. So this relation, it works in all integers. So we have, what do you call this? Relation class, right? Where is it? A relation class. So relation class 1 and relation class 2 defines a partition of the input subset. What do you call the subset that is being used? Set A. This set which the relation is acting on, what do you call that set? I'll call it the input set. So set the relation class 1 and relation class 2 together, they like partition of the, together they make the partition of the input set. Define an equivalence relation on a set A from the partition 1, 4, 2, 3, 5. Define an equivalence relation. So hold on, let me think about this. Two point six point 22. We have set a 1, 2, 3, 4, 5. And the partition is 1, 4, 2, 3. Five. So like suppose we have one class. So there should be a class, like a relation class where we have 1, 4 as one of them and 2, 3, 5 as one of them. Uh yeah, this is confusing. And they need an equivalence relation as well. So this cannot be 2, 3, or 5 because in an equivalence relation we need what do you call it? Reflexive, yeah. If it's reflexive, like if we have something like this, then it has to be a reflexive relation, right? So 2 cannot be here. 3 or 5, the 2, 3 or 5 has to be here, 1, 4 has to be here. But if 1, 4 is here, if 1 is related to 4, for it to be symmetric, then 4 has to be related to 1 in that relation. Similarly, over here, 2 related to 3, 3 has to be related to 2. Same for 5 and 3. So, also it has to be transitive. So, if 2 is related to 3, 3 is related to 5, then 2 has to be related to 5. Let me think about this. This is plus 1. What about prime? Is prime maybe? Prime and not prime. Ah, okay, let's define a relation. Like it's an if this is a prime, then this is also a prime. If this is not defined as a prime, then this is not yeah. So I will define a relation A B if A is prime, then B is prime. If A actually it has to be like this. So if 2 is prime, then 3 is prime. If 3 is prime, then 5 is prime. If 5 is prime, then if 2 is prime, then 5 is prime. I think 2 goes here, so does 3 and 5. 1 goes here, 1 is not prime, so 4 is not prime. I think that is one solution. We also have 1, 1, 2, 2, and so on, since every number is in the same subset as itself. Should I read the next chapter as well? How big is the next chapter? Okay, it doesn't seem big. Matching in a bipartite graph. Given a bipartite graph, a matching is a subset of edges for which every vertex belongs to exactly one of the edges. Every vertex belongs to one of the edges. A matching is a subset of edges for which every vertex belongs to exactly one of these edges. Uh, Hold on, I'm confused. Every vertex belongs to exactly one of the edges. Does the graph below contain a matching? If so, find one. Not all bipartite graphs have matching. Draw as many fundamentally different examples of bipartite graphs that do not have matchings. So every vertex belongs to exactly one of the edges. So it's a subset of edges, right? So vertex cannot have multiple edges. A vertex can only have one edge, right? Every vertex belongs to exactly one edge. Okay. Can I? Yeah, let's just copy this. I'll just redraw it just in case. So we have this 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5. Yeah, 2 and 3. 2, 3, 4. And let's just draw these lines. Lines is easier. This, 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 this. So for the third one is straight down, and the fifth. Is that right? You have this here. I think if I go randomly, I will get confused, but I don't care. So it's not directly down. It's here. And it's on the second one. So 3, 2, 2, 3, 2, 3, 3, 2, 3, 2, 4, 1. Right. So I need to start deleting edges, right? So I can delete this one and this one. And I can delete this one and this one. And this one, this one, this, this. And this one is an issue. No, no, it's not an issue actually. Yeah, this is a matching, right? Every vertex belongs to one edge. Suppose you have a bipartite graph G. This will consist of two sets of vertices A and B with some edges connecting some vertices of A to some vertices in B. But of course, no edges between two vertices both in A and or both in B. A matching of A is a subset of the edges for which each vertex of A belongs to exactly one edge of the subset. And now vertex in B belongs to more than one edge in a subset. In practice, we will assume that number of elements in A is equal to number of elements in B. The two sets have the same number of vertices. So this says that every vertex in the graph belongs to exactly one edge in the matching. We are calling a matching, what we are calling a matching is sometimes called a perfect matching or a complete matching. This is because it is interesting to look at a non-perfect matching as well. Some context might make this easier to understand. Think of the vertices in A as representatives in a class and vertices in B as representing presentation topics. Put an edge from vertex A to vertex B if student A would like to present on topic B. Of course, some students would want to present on more than one topic, so their vertex would have degree greater than 1. As the teacher, we want to assign each student their own unique topic. Thus, you want to find a matching of A. You pick some subset of edges so that each student gets matched up with exactly one topic and no topic gets matched up to two students. The question is, when does a bipartite graph contain a matching of A? To begin answering this question, we will consider what could prevent the graph from containing a matching. This will not necessarily tell us condition. The graph does have a matching, but at least it's a start. One way G could not have a matching is if there's a vertex in A not adjacent to any vertex in B, so having degree 0. What else? So what if two students both like the same topics and no others? Then after assigning that one topic to the first student, there's nothing left for the second student to like. So it is very much as if the second student has degree 0. Or what if three students like only two topics between them? Again, after assigning one student a topic, we reduce this to the previous case of two students liking only one topic. Should be clear at this point, if the group of n students who as a group like n minus 1 or fewer topics, then no matching is possible. This is true for any value of n in any group of n students. To make this more graph theoretic, say you have a set, you'd say you have a set S, which is a subset of A of vertices. Define N S to be a set of all the neighbors of vertices in S, that is in S. So NS is a set of neighbors of vertices in S. Set of all neighbors of vertices. Say you have a set S, which is a subset of A. Define S to be all the neighbors of, but okay. So S is a subset of A, and NS is a set of all neighbors of S, all neighbors of vertices in S. Contains, okay, NS contains all the vertices that are adjacent to at least one of the vertices in S. NS is a set of topics liked by students of S. Other discussion can be summarized as follows. In a bipartite graph, GAB has a matching A, has a matching of A, then the neighbors of S is larger and greater than the number of elements of S for all S which is a subset of A. Every set of vertices has at least as many neighbors as vertices in the set. Does that mean that there is a matching? Surprisingly, yes. The obvious necessary condition is also sufficient. This is a theorem first proved by Philip Hall in 1935. Let G be a bipartite graph with sets A and B. Then G has a matching of A if and only if the set the number of elements in S is greater than or equal to S. Number of elements in S. For all S, which is a subset of A. Shouldn't graph be defined as vertices and edges? An ordered pair of vertices and edges. There are quite a few different proofs of this theorem. A quick internet search will get you started. In addition to its application to marriage and student presentation topics, matchings have applications all over the place. We conclude with one such example. Suppose you deal 52 regular playing cards into 13 piles of 4 cards each. Prove that you can always select one card from each pile to get one of each of the 13 card values: ace, 2, 3, 10, jack, queen, and king. Prove that you can always select one card from each pile. Suppose you deal 52 cards into 13 piles of 4 cards each. 13 piles of 4 cards each. Wait, hold on. How can we prove this? Suppose we have a graph. Example 2.7.2. We have A's. This is a vertices 2, 3, 2, 3, 4, 5, 6, 7, 9. There's no 10, right? There is a 10. Jack, Queen, King. Then we have 13 pile. No, 13 pile, 4 cards each. Yeah, yeah. So pile P1, pile 1, pile 2, and so on. They would have 4 cards, right? So one possible way is like this over here. 1, 2, 1, 2, 3, 4. One possible way for P2 is like 1. But hold on a minute. 52. No, I don't think this is the right graph. And let me see the solution. Doing this directly would be difficult, but we can use a matching condition to help construct a graph G with 13 vertices on set A, each representing one of 13 card values, and 13 vertices in set B, each representing one of the 13 piles. Eight, 8 to 10, 13, and I was just trying to represent 13 piles. Yeah, that is what I was trying to do. Draw an edge between A to B, and that is what I was trying to do. If a card with value A is in pile B, okay. Notice that we are just looking for a match of A. Each value needs to be found in the piles exactly once. But the thing is, there are multiple colors of the cards, right? So a red A, black A, like there are 4 different aces, right? Each of them could be in pile 1. We will have a matching if the matching condition holds given any set of card values. A set A, which is a set S, which is a subset of A, we must show that the neighbor of S is larger, greater than or equal to the number of elements in S. That is, the number of bytes that contains those values, it is the number of different values. But what if it wasn't? Let's say an element of S is equal to K, and the number of the neighbors is less than K, then we would have fewer than 4K different cards in those piles. But there are 4K cards with K different values, so that at least one of these cards must be in another by a contradiction. Thus, a matching condition holds, so there is a matching as required. Okay, this last part was kind of confusing. So I will end the stream here, and I may read a different, like I will keep reading this book. I may read a different book as well alongside this, or I may keep reading this book. We will see. Anyways, I'll end the stream here then. Anyways, see you guys later. Bye.